if you look at the calculation done for the bowling ball problem, you'll notice that you can come up with a very similar expression doing things in the opposite order. Say, what's the bowling ball's acceleration towards the Earth? And if you apply the second law and the law of gravity together, you'll come to this amazing result that relates the gravitational constant, the universal gravitational constant, to the acceleration near the surface of a planet or any object you live on. So what does this equation say? This is a big one. This is a big deal. What we're saying here is that, let's try that again. Get this nice and properly boxed in. All right. So what you're saying is that if you live on a planet of mass m and it has some radius r, as long as you're near the surface, as long as you're near, one radius away from the center of that planet, you're going to fall at some rate little g. So one thing I want to make clear here is that g will change depending on if you go to the moon or you go to Mars or if you could somehow possibly do it Jupiter. All right. So as points of comparisons, we can determine your weight on other celestial objects. And here's what this handy chart's for. So every single one of these values are going to be relative to Earth because, we're biased human beings. So everyone's going to be measured in terms of Earth radii, Earth's mass, and accelerations relative to our weight, our acceleration on Earth at 9.8. This last column here will be the explicit accelerations in meters per second squared. So let's go through this. The moon. The moon's about a quarter the size of Earth and 0.01 the mass. And that combination will end up netting you an acceleration that's about 17% of what we feel here on the Earth. So have you ever seen videos of astronauts on the moon when they're doing those kind of silly looking hops around? That's because they've discovered that was the easiest way for them to maneuver on the moon. Because they had enough force that they could produce to give them these fanciful bounces. Now, continuing down the chart, let's say, hey, we sent a manned mission to Venus. Venus was once used to be described as like our Earth's twin sister in the Pantheon. And it turns out this was pretty close. Venus is almost the same size as Earth, 95% the size of Earth. And the mass, not too different. Just 0.82 Earth masses, which gets you to an acceleration of 0.9. So if you move to Venus, you'd feel about 10% lighter. Not bad. Sucks that Venus is a hellscape of temperatures and gases, lots of carbon dioxide and violent storms, but that's a discussion for a future section. Mars is the next big one, because we're always now hearing about discussions of Mars. And Mars is about half the radius, about 11% Earth's mass. And you'll get an acceleration on Mars that's about a third of what you feel here. And you science fiction fans, John Carter, the whole premise was a human, a man getting up on Mars and basically becoming a gladiator, a superhero, because of how much stronger he was compared to the native Martians. And that was all based off of this kind of ploy, this idea here. Continuing on with our discussions about gravity, we come to a weird one that we have to describe as the principle of equivalence. So let me set up the problem. How do we mass something? How do you know how much mass something is? And you like to think of it as, well, you get on a scale and you say, what's your weight? But the scale, how much you weigh, well, go back to the last slide. That's going to depend on what object you live on. So we could instead apply a force. Remember the hit boxes from the previous section. If I hit something, apply a force, and measure its acceleration, that can give me its mass, or say its mass is given as the ratio of force per acceleration, and we call it its inertial mass. Well, a completely different way for me to measure the mass of something is say, well, let's just let gravity act on it, right? in principle, these are different ideas. These are different concepts. This just says hit something, see how far it moves. This says put them in orbit, right? Let gravity act on these things. And so you could say that the gravitational mass is just the product r squared F gravity divided by gm, where m's the mass of the planet you live on. And there is nothing that says these two, the inertial or the gravitational mass, have to be the same. There's nothing in the laws of physics that make them the same. This is an open-ended question in physics. We, to the best of our knowledge, we believe in the same thing. Our experimental measurements, to our highest level of precisions, have confirmed these different types of definitions of mass do agree. But nothing in the universe says that they must. So that's one of the weird quirks when you're talking about mass. Never just assume that you fully understand something. There's always going to be some subtleties and nuances hidden. Another weird thing talking about gravitational forces is this concept of self-gravity. The law of gravity just says that if you have two masses, there's going to be a force between them. So think about a planet like Earth. Here you have Antarctica. Well, that's a massive body, and it's separated by some distance to, say, Africa. So there's a force between Antarctica and Africa. Well, similarly, there's a force between, say, Africa and the North Pole, or Africa and the Americas. So you have this massive object that's composed of all these isolated masses, the different continents, the oceans, and they're all tugging and pulling on each other, and the summation of all these forces is what we call the self-gravity. All right? So the self-gravity is producing all the forces that's holding a planet together. So some important consequences of this. If you are massive enough, if you have enough mass, gravity will squeeze and compress all your different components enough to make you a sphere. This will come up later when we talk about the definitions of what is a planet. You have to be spherical. It turns out to mean that you need enough self-gravity to squeeze yourself into a sphere. If you want to think further on, you can think about stars. Right? Stars have a large self-gravitational pull, a lot of mass stacked on top of each other. It's just that stars happen to have so much that in their core, they're going to start squeezing atoms together through a process called fusion. And that's the basic definition of a star. So let's come back to this. Let's focus on planets, and let's talk about a special case of spherically symmetric bodies. Right? When calculating the law of gravity, in all of our previous examples, we haven't said, well, you got to account for the mass way out here versus a mass way out here, right? You just say, look, all you've done is treat your mass on the edge of the planet, on the surface of the planet, and you said, put all of Earth's mass at some point, some tiny point at the center of planets. And this turns out to be a real correct model. All right. In this case, this is called a spherically symmetric body. You take a big sphere, have all the mass distributed throughout that sphere, and you say, all right, what's the force on this chunk? What's the force between you and this chunk? Force between you and this chunk. And you sum all that up. You take all of these forces added together, and it's equivalent to as if Earth was a hollow shell with all of that mass concentrated right here at the center. Right? So this is a consequence of self-gravity, that we can treat planets as being these point particles at the center, at their center of mass. Now, speaking of center of mass, I have a excellent demo to try and give you an idea of what the heck I mean by center of mass. So let's go look at some weird consequences of the center of masses. So we can talk about how gravity acts on the center of mass. And I'd like to have a video to demonstrate what we're talking about. So for starters, we'll start with easy, a spherically symmetric tennis ball. And the center of mass will be the center of the ball. Now watch the motion, okay? I toss it up, back down, up, down, up, down. Pretty easy. Right. Now let's switch to something that is definitely not spherically symmetric. So what this is a wooden block. This side has some extra weight in it. We've embedded extra weight in this side. So this half is going to be a little bit heavier. The glowing spot, that represents the center of mass of this whole thing. And I'm going to give this thing a toss up. You're going to see the whole block do some crazy twists, but watch what the dot is doing, the center of mass. Right? It's still doing the same trajectory as the tennis ball. The dot is going to go up, 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 stop, fall, fall, fall. Exact same trajectory. One more time. So even though the object, we'd call it an extended body, has some strange geometry, gravity will still act on the center of mass.